Also notice that the order of the symmetric group in letters is the number of permutations of n objects taken n at a time, which is n factorial. So let's look at an example. The order of the symmetric group on 2 letters is 2 factorial, which is 2 times 1, or 2. So there are 2 ways to choose the first number, and 1 way to choose the second number once the choice of the first is made. And so the integer 1 can be mapped onto either the integer 1 or the integer 2, in which case we, in the first map, that means that 2 is mapped onto 2, and in the second map, 2 is mapped onto 1. And so there are 2 elements in the symmetric group on 2 letters. So we can represent 1 by the identity, which is the map from 1 to 1 and 2 to 2, and the second one we'll call pi, and this is the map from 1 to 2 and then 2 to 1. So notice that I squared can be represented as the product of the 2 permutations whereas this is a composition. We apply the map on the right first, so that 1 is mapped onto 1, which in turn is mapped onto 1. 2 is mapped onto 2, which in turn is mapped onto 2. So no surprise here, I squared is I. Now we'll look at I times pi. So again, we apply the map on the right first. So 1 is mapped onto 2, which in turn is mapped onto 2. 2 is mapped onto 1, which in turn is mapped onto 1. And so this is pi, no surprise there either. So now we look at pi times I. Applying the map on the right first, we have 1 is mapped onto 1, which in turn is mapped onto 2. 2 is mapped onto 2, which in turn is mapped onto 1. And so pi times I is also pi. So we look at pi squared. One is mapped onto 2, which is in turn mapped onto 1. 2 is mapped onto 1, which in turn is mapped onto 2. So this is the identity. Okay, new definition. A graph, and I'll use a cursive letter G, consists of a set V of elements called vertices or nodes, and a set E of elements called edges, each edge has 1 or 2 vertices associated with it, and an edge is said to connect its vertices Now, a directed graph or digraph for short is a graph for which the edges have a direction So, for example, in the symmetric group on 2 letters, the identity can be represented by the digraph, where 1 is mapped onto itself, 2 is mapped onto itself, and so we have an edge that takes the element back to itself. We call this a loop. And the permutation pi can be represented by the digraph, where the element 1 is mapped onto the element 2, and the element 2 is mapped onto the element 1. We call this a cycle. Notice that we begin at the node or vertex 1, and then arrive back at the vertex 1. Okay, so let's look at another example. The order of the symmetric group on 3 letters is 3 factorial, which is 3 times 2 times 1. There are 3 ways to choose the first element. After that choice is made, there are then 2 ways to choose the second element. And once that choice is made, there is 1 way to choose the third element. So if we look at the possible maps, the element or the integer 1 can be mapped onto itself, or it can be mapped onto the integer 2, or it can be mapped onto the integer 3. And once that choice is made, we have 2 choices for the second element. So in the maps of 1 onto 1, we have the choice of 2, 3 or 3, 2. On the maps, or for the maps where the integer 1 is mapped onto 2, we have the choice 1, 3 or 3, 1. And for the maps of the integer 1 onto the integer 3, we have the choice 1, 2 or 2, 1. So let's first focus on the permutations that leave the integers in their proper order. That is 1, 2, 3, 2, 3, and then back to 1, 3, then to 1, and then 2. Let rho sub naught be the identity. Rho sub 1 is the map from 1 to 2, 2 to 3, and then 3 to 1. And rho sub 2 is the map from 1 to 3, 2 to 1, and then 3 to 2. Now let's look at the maps that leave an element fixed. For instance, in this map, the first element is fixed. In this map, the third element is fixed, and in this map, the second element is fixed. So let mu sub 1 be the map that fixes the first element. And so this is the map from 1 to 1, 2 to 3, and 3 to 2. Let mu sub 2 be the map that fixes the element 2. And so we have 1 to 3, 2 to itself, and then 3 to 1. And finally, let mu sub 3 be the map that fixes the element 3 and exchanges 2 and 1. So let's look at the digraphs. So for the identity, we have 3 loops. For row sub 1, 1 is mapped onto 2, 2 is mapped onto 3, and then 3 is mapped onto 1, so we have a cycle. And now if we look at row sub 3, row sub 2, in row sub 2, 1 is mapped onto 3, 2 is mapped onto 1, and 3 is mapped onto 2. So 1 is mapped to 3, 3 is mapped to 2, and 2 is mapped to 1. So we have a cycle here. Now let's look at the digraphs for mu sub 1, mu sub 2, and mu sub 3. So the map mu sub 1 fixes the first element and exchanges the other two, so that we have a loop on the vertex 1 and a cycle from 2 to 3 and then back to 2. So now mu sub 2 is the map that fixes the second vertex and exchanges the other two elements, so that we have a cycle from 1 to 3 and then 3 to 1. And then finally for mu sub 3, this is the map that fixes the third vertex and exchanges the other two, so that we have a cycle from 1 to 2 and then 2 to 1. So let's look now at what we call cyclic notation of permutations. And we'll look at mu sub 1, mu sub 2, and mu sub 3 first. Now for cyclic notation, we show the complete cycles and leave out the loops. So for instance, in mu sub 1, we have a loop from 1 to itself and a cycle from 2 to 3 and then 3 to 2, and we represent this way, 2, 3. This is the cycle that takes the element 2 to the element 3 and then the element 3 back to the element 2. And if an integer is not represented in a cycle, that means that it is a loop. So in this example, 1 is mapped onto itself. So for mu sub 2, we have 1 mapped onto 3, which in turn is mapped back on to the integer 1. And so we have this cyclic notation. And for mu sub 3, we have 1 is mapped to 2, where 2 is mapped back to 1, and the element 3 is mapped onto itself. So now if we look at row sub naught, row sub 1, and row sub 2, for the identity, each element is mapped onto itself, and so we usually represent this way, where it shows that the element 1 is mapped onto itself, and this also implies that 2 is mapped onto itself and 3 is mapped onto itself. In the map row sub 1, or the permutation row sub 1, we have 1 being mapped onto 2, which is mapped onto 3, and 3 is mapped back onto 1. And in the map row sub 2, we have 1 being mapped onto 3, which is mapped onto 2, which is in turn mapped back onto 1. So let's look at multiplication of the elements in cyclic notation. So we'll look at row sub 1 times mu sub 2. This is the cycle 1 to 2 to 3 back to 1 times the cycle from 1 to 3 and back to 1. Again, multiplication is really the composition of two maps, and so we always apply the map on the right first. So if we start with the element 1, 1 is mapped onto 3 in the first map, and then is in turn mapped back onto itself, and so 1 is cycled out. So now we start with 2. In the first map, 2 is fixed, so 2 is mapped onto itself, and then 2 is mapped onto 3. So we start with the element 3. 3 is mapped onto 1 in the first map, which in turn is mapped onto 2, and so that completes the cycle. And so this is the cycle 2 to 3 back to 2, and this is the map mu sub 1. If we look at the product mu sub 2 times row sub 1, and this is the cycle 1, 3 times the cycle 1, 2, 3. So we begin with 1. 1 is mapped onto 2 in the first map, and in the second map 1 is fixed, or rather 2 is fixed, so it is mapped onto itself, and so we go from 1 to 2. So now we start with 2. 2 is mapped onto 3 in the first map, and then in the second map onto 1, and so that completes the cycle. If we start with 3, 3 is mapped onto 1 in the first map, and 1 is in turn mapped onto 3 in the second, so 3 cycles out. And so this is the cycle 1, 2, which is mu sub 3. So new definition. A permutation pi is even if and only if it can be expressed as an even number of even cycles Otherwise, the permutation pi is odd. So let's look at an example. In the symmetric group on 3 letters, row sub naught can be represented as the cycle of 1 onto itself, or the loop of 1 onto itself. Row sub 1 can be represented as the cycle from 1 to 2 to 3 and then back to 1, and row sub 2 can be represented as the cycle 1 to 3 to 2 and then back to 1. Each of these is has 0 even cycles, since in the first example we have a cycle of length 1. In row sub 1 we have a cycle of length 3, which is odd, and in row sub 2 we have a cycle of length 3, which is odd. So there are 0 even cycles, and so Rho sub naught, rho sub 1, and rho sub 2 are even permutations. And mu sub 1 is the map that leaves 1 fixed and maps 2 onto 3 and 3 back onto 2. Mu sub 2 leaves 2 fixed and maps 1 onto 3 and then 3 back onto 1. And mu sub 3 leaves 3 fixed and maps 1 onto 2 and then 2 back onto 1. Now each of these has one even cycle. Each cycle is of length 2, which is even, and there is one cycle, so an odd number of even cycles. And so mu sub 1, mu sub 2, and mu sub 3 are odd permutations.